Hi everyone, welcome back. So with this video we're going to continue looking at how we generate electricity, and we're going to introduce a new concept in this video which are going to help us later on when we look at electric generators, and this is the concept of flux. So magnetic flux, we define the magnetic flux to be the amount of magnetic field passing through a particular area. Okay, this is just going to be our working definition for now. We're not going to get too into depth about what flux is and all this stuff and how it's related to magnetic field. We're just going to say the flux is the amount of field passing through a particular area. Okay, and it's very easy to calculate, especially when the when the field is perpendicular to the area. You can express the magnetic flux using this little relationship here. Okay, magnetic flux, which is this symbol on the side, which we call phi, P-H-I, it's a Greek symbol. Phi equals B times A. And this little upside down T, that just means perpendicular. So this is the case when the field is perpendicular to the area. And we'll see a picture of what that looks like in a second. So B is the strength of the magnetic field and A is the area that is perpendicular to the field. You just multiply them together. Okay, simple as that. That is how you calculate this thing called flux. Magnetic flux has units of Webers, which we signify with WB, capital W, lowercase b. And later on, when we start dealing with Faraday's law and things like that and Lenz's law, we're going to treat flux as a vector. Okay, technically magnetic flux is not a vector, but we're going to pretend that it is, and the way that we're going to do that is we're going to define a face of the area to be positive, and you'll see what I mean by that in a second. Cool, so there's this new thing called magnetic flux, and it is equal to the magnetic field strength passing through a particular area. Alright, so here's a picture. Alright, and let's just look at the first picture for now. So we've got this area defined by some kind of borders. They could be physical or not. And you've got this field going through it, okay? Now, when I say that the field is parallel to the area, perpendicular to the area, I mean that the plane of the area. So if you pretend this area is like a sheet of paper, the sheet of paper is perpendicular to the arrows of the magnetic field. Okay, if you've got something like that, then you can just multiply the field and the area together, and that gives you your flux. Things get a little bit more complicated though when they're not perpendicular. Okay, and you won't really have to deal with this too much, but just so you know about it, the flux can be written technically as B times A times cos theta, and theta is the angle shown in the diagram. Okay, so it's this angle here between this vector sticking out perpendicular to the area and the magnetic field lines. Okay, so when you start sort of rotating this area a little bit, you'll notice that this perpendicular vector to the area, this arrow here, okay, you take the angle between this arrow and the field lines themselves. Okay, so that angle there is theta. If you want to work out the flux, then you do B times A, but you also multiply by this cos theta to account for the fact that there is technically less area that the flux is going through. Okay, think about it. If you rotate this area a little bit, and you sort of, I guess what you could do is cast a shadow on that area. So pretend it's a piece of paper and you're rotating the paper. Cast a shadow of that paper in the direction that the field lines are traveling. That shadow is going to appear smaller than it would if the paper was perpendicular to the field. Okay, so you can imagine that the magnetic flux would be smaller in that case because there's technically less area for the field lines to travel through. And this is in the limiting case when you rotate this by 90 degrees, the angle between the area and the magnetic field lines is 90 degrees. And what's cos of 90 degrees? 0. Okay, so there is no flux. There is no field lines going through this area in this case. All right. Most of the time we're going to be dealing with this case and this case. And you can sort of fill in the gaps, I guess you could say, about what happens when you go from here, rotating it by some angle and get to here. Okay, so we won't really have to deal with this cos theta, but just so you know that it's there, that's how you would use it. Okay, cool. So magnetic flux is maximum when the plane of the area is perpendicular to the field, and it is a minimum, or zero, when it's parallel to the field. Okay, and it's some value in between when the angle is somewhere between 0 and 90 degrees. So let's do a question. A student places a horizontal square coil of wire of side length 4 centimeters into a uniform vertical magnetic field of strength 0.05 Tesla. How much magnetic flux passes through the coil? We can draw a picture of this. So we know that the field lines are vertical. Doesn't really matter if it's up or down, let's just call them up. And I'll use another color for the area. So we've got a coil of wire, square coil of wire. Like that. Okay, so the field is going up through the coil. It's a square coil. This has a side length of 4 centimeters, which is equal to 0.04 meters. Now the question is, what is the flux passing through the coil? Okay, very easy to calculate, especially when they're perpendicular to each other. So the flux is equal to the field strength times the area. In this case, the field strength is 0.05 Tesla. And the area of this square coil is just 0.04 meters times 0.04 meters, 0.04 meters squared. And we can work that out, and you end up getting something like 8 times 10 to the negative 5 Webers. Okay, there you go. Fairly straightforward to calculate flux. Not too much to it. All right, moving on. So the next question is related. It says the student then rotates the coil so that after 90 degrees, the coil is vertical. If the student keeps rotating at a constant rate, draw the graph of the magnetic flux versus time for 2 whole rotations. Horizontal units are not necessary. All right, so let's set up an X and Y axis. So the Y axis we will call our flux, and the X axis will be time. All right, so just quickly, let's go back to the picture we had. So you can imagine that what's going on here is this coil is on some kind of rotation axis like that, okay? And the student then rotates the coil along that axis. And so after 90 degrees, the coil would be vertical. Now, can you think of what would happen to the flux in that position? Well, you'd get some picture that looks something like this. The third picture down here, okay? The coil would be parallel to the field lines, so there would be no flux, okay? So if we were to start drawing our picture, let's draw our graph starting from the position in the previous slide, okay? So the position in the previous slide, we have a maximum amount of flux, and the angle between the area vector, I guess you could call it, and the magnetic field lines is 0 degrees. After 90 degrees, we know that the flux would decrease to 0. Okay, so after 90 degrees, the flux becomes 0. Okay, let's just put in brackets 90 degrees. Okay, after another 90 degrees, what do you think is going to happen? So now we're at 180 degrees. Okay, think about it. You're rotating this coil, and this is where I say it comes in handy to determine a direction for the magnetic flux. So let's determine this side of the coil to be the positive side, okay? So as of right now, the flux is coming out of the positive side, okay? If you were to then rotate the coil 180 degrees, what would happen is this arrow would then be upside down, and it'd be going out the bottom of the coil, right? So the field lines are opposing the direction here, and so what we would say is that the flux can be considered to have a negative value. So the actual sort of, I guess what you could say, the absolute value of the flux is still 8 times 10 to the negative 5. It's still a maximum value. It's just in the other direction. So let's call that negative. Okay, we'll call it negative 8 times 10 to the negative 5. So what would happen is you'd get a flux that has a value of negative. Negative 8 times 10 to the negative 5, and this one would be 8 times 10 to the negative 5. All right, cool. After another 90-degree rotation, so now we've rotated 270 degrees, well, our coil is just going to be in this position here again, this third position where they're parallel to the field. So you'd have no flux again. So it's similar to what happened at the 90-degree position. So now our point is here. And then after another 90-degree rotation, we end up back where we started, which we know is going to have a maximum flux here. Okay, so if we've now rotated our coil once, okay, 360 degrees. And what we could do is just continue this again for another rotation. So I'll extend this axis. So this goes out a little bit more. And where's my pen? Come on. Okay, and then you start again. So after another 90 degrees, your flux is 0. After another 90 degrees, your flux is maximum, but in the opposite direction. After another 90 degrees, your flux is 0 again. And after another 90 degrees, you get back to where you started. Okay, let's connect the dots. Okay, and we're not going to connect them just as we see them here. We're going to connect them in a very special way. And that will become apparent in a second. This might already look familiar to you. We're talking about something that has an angle, okay? And this graph might remind you of something if you do methods. Yes, that is a sinusoidal looking graph. In fact, the way that this graph is, it's a cos graph. Okay, and it has a shape that looks something like this. Why does it have this shape? Well, if you remember back to our definition for flux, okay, our flux can technically be described using this relationship here, where we have this cos theta in our expression. And the cos theta part, well, if you really think about it, the flux is determined by the angle. Okay, so really this flux is a function of the angle. And so if it's a function of cos theta, that means the graph that you get is going to be a cos graph of some kind. The shape, we just call it sinusoidal. So that's the graph of a flux versus time graph. And it is a flux versus time graph because depending on the time, if you're rotating your coil at a constant rate, then the angle that it makes with the field is a function of time. Okay, so even though our flux is dependent on the angle, really the angle is dependent on the time, so the flux is dependent on the time. Okay, so that's why we can call it a flux versus time graph, even though we've described it with angles here. And there we go. Okay, that's your flux versus time graph, and this is what you're going to see pop up time and time again when we deal with generating electricity, because the way that you generate electricity is through something similar to what we've described here, which is rotating a coil, a conductive coil, through a magnetic field. Okay, and we'll see later that that produces an EMF and produces alternating current. Okay, so quick summary, we'll stop here. Magnetic flux, okay, phi, is defined as the amount of magnetic field passing through a particular area. It can be calculated using this expression here. You've just got to remember that when you're using this expression, you're talking about the perpendicular field. Okay, most of the time you'll be talking about the field will be perpendicular to the area. If it's not, then you just add a little cos theta in there. Okay, which is basically the component of the field which is passing perpendicular through the area. Okay, you can split it up using trigonometry, and you'll see that's where your cos comes from. And just remember, the flux is a maximum when the field is perpendicular to the area, and 0 when the field is parallel to the area. And just as a final point, it's helpful to remember, or helpful to say that flux has a direction. Okay, and that's determined by setting up a direction for the area, and if the field is pointing in the same direction as the area, you can say that the flux is positive. If the field is pointing in the opposite direction to the area, then you can say that the flux is negative. Okay, that's going to come in handy later on when we talk about EMF. Okay, so that's it. We'll stop there, and we'll see you next time.